Hello, and hello, I'm Chris Weir from the Midlands Aerospace Alliance, and I'm here to speak to you today on the Environmental Sustainability Challenge for Aerospace. So, just briefly on myself, I have 30 years, well, over 30 years now, experience in aerospace, and a number of my products that I associate myself with are on the screen. But I think really what's important, and some of the messages that we'll get out of today, you don't get something for nothing is really a fundamental engineering rule that I think has never been broken in my career. And really the aspirational search for striving for simplicity is always an optimal goal. And when we're looking at introducing new items versus existing items, anything that's called similar means that it's different and should get a lot of attention, and we should remain curious. I'm also a bit of an addict for lean, and always believe there's a better way and faster way of doing things, and that handoffs and where we pass over accountability are points of weakness in any process. But ultimately, I also believe that learn by listening, reading, and doing, and I'm still working on the listening. So, today, anyway, more importantly, get on to the subject of today. So I thought we ought to discuss the problem statement first, and then get into some of the strategies as a solution for what I would term Jet Zero, that is reducing or eliminating the emissions from aircraft, and then talk about the role of the engineer and what this means in a net zero business, and then we'll try and pull that all together. So the problem statement, well, I think we all know this, so I won't spend too long, but since the 50s, we've seen an increase in fossil fuel emissions going up 7 times in 7 decades. And this is just the emissions from the CO2 generated from fossil fuel. And we now have convinced ourselves that the global temperature is linked to this, but there is a lag as well. So even if we froze the output of greenhouse gas emissions instantaneously, we'd still see an increase in global temperature. And the latest IPCC report is sobering reading, shall we say. So as with respect to aircraft, it's absolutely appropriate that we consider greenhouse gas emissions, your carbon dioxides, methanes, nitrous oxides, fluorinated gases. And these are the ones that Kyoto Protocol defined as greenhouse gases. And typically you see them summarized as measures of tons of CO2 equivalent. So they're sort of standardized into a standard measure. But in aerospace, we also need to consider the impacts of NOx and smoke and water vapor that turns into contrails. So, and that's something the industry has actually been working on reducing for some decades now. So let's have a look at aviation fuel burn by sort of sector and the amount we get through. It's quite a thirsty industry. Global annual aviation fuel burn in 2019 was 401 billion litres. There are predictions that this will increase. I think most predictions assume there's going to be some sort of growth in air travel. Therefore, no surprise, by 2050, if we do nothing else, apart from just modestly improve the performance of engines, we'll be increasing the amount of fuel we burn. Estimates do vary, but typically doubling from where we were in 2019 are typical. Just to give you a bit of a flavour, back in before the pandemic, London Heathrow Airport was getting through about 22 million litres a day of aviation fuel. The chart on the right just shows which sectors are spending this. So your small turboprops and regional jets and business jets really account for some 7% or so of fuel burn. The area we really want to focus on is your sort of single aisle, narrow body, sometimes called your A320s, A220s, Boeing 737s, etc. Typically, reasonable short haul that you go on holiday to, or your sort of transatlantic wide body aircraft, Trans-Pacific, Twin Aisles, and they're 57%. So those are really the ones that we want a solution for. So really, if we summarize the problem statement, today the majority of commercial aircraft burn Jet A1 fossil fuel, Jet A fuel, whatever you want to call it, aviation fuel. And as I said, narrow body and wide body aircraft account for 93% of this approximately. Aviation is still predicted to grow, and the improvements in aircraft and flight operation efficiency alone won't actually reduce this fuel burn. So clearly there is a problem statement. We need to do something about this, and that's really where we're going to go to next. Apart from one point I'd like to make, and it's a kind of sobering point. If you look at the global greenhouse gas emissions due to humans, in 2019, this was some 52.4 gigatons of CO2, and if we cut out the global transportation, it's approximately a fifth, and then aerospace is about 2.1%, give or take, of that. So clearly, you could argue that aerospace is or aviation is a relatively small impact on global emissions. But there's 2 points here worth highlighting. Number one, this is actually an issue because it could actually be a factor when people are considering where to make the investments and prioritizing them. And number two, as other areas improve, if aviation does nothing, then it will become a larger proportion of the problem. So what are the strategies for actually low or zero emission aircraft? Well, I'm going to actually spill the beans and come up front, and this is a bit of a spoiler chart really, but the way I see it is there's actually 4 key strategies, the 5th strategy being stop flying, but I haven't considered that one in any detail. But to obviously, one approach is to reduce fuel burn, another is to buy sustainable fuel, a net zero fuel as I've called it. Don't burn fuel, find another means of powering your aircraft, and don't burn fuel that contains carbon. So, and as you see, all the answers are there, but we'll come on to those individually. So let's look at reducing fuel burn. There's two items here really, is aircraft operations and the actual airframe and engine itself. So I was just thinking about flights you've had. Certainly these are rhetorical questions, but have you ever been told about your airline's excellent record for on-time departure from the gate? Some very impressive numbers are quoted. But I would add to that is, have you ever been on board an aircraft sitting in a queue on the runway prior to takeoff? I have done that in certain cases for over an hour. And in one case, we actually had to turn back and refuel. So I think perhaps gate departure isn't really the right measure for sustainability. Perhaps we should be thinking about the emissions produced during ground taxiing and setting some standards against that. The other one that really frustrates me is that, have you ever been told that your aircraft will arrive early at your destination? Well, around busy airports, that usually means only one thing, and you end up circling around. And again, this is where you're waiting for a slot to land because you've turned up early, and essentially it's a very inefficient way of operating an airframe, and you're burning more fuel. So perhaps we should measure on-time schedule arrival, or maybe the fuel burn used in the flight. But I think there's lots of scope for operational improvements, and indeed there are activities ongoing that could, with immediate effect. Some quotes say 5 to 10% difference. I wouldn't argue with that. I think this is a massive opportunity. There are more technically challenging concepts about flight paths, etc. But those two can be readily introduced. What's more challenging and more difficult is when you want to actually improve the efficiency of the airframe. Now, I have an aero engine background, more on the equipment systems, but supporting aero engine manufacturers as well as airframers. But so I'm going to focus on engine performance largely. But as you see, we actually have you could argue, a proud history of reducing fuel burn. And I also emphasize that the industry has been very active on reducing NOx emissions and smoke emissions as well. I mean, over the last 10 years or so, $150 billion of R&D has been spent to improve the engines alone. And so it's a big factor. However, one thing we do notice from these charts is it's starting to get more difficult to really get its significant steps in efficiency. What the engine manufacturers are looking at now is improving propulsive efficiency. So essentially, you've got two options with a gas turbine. You can either focus on thermal efficiency, where we've seen approximately 0.4% per year improvement since the 70s, and that's really around the combustion turbine area and running it as hot as you can without affecting life, and also giving consideration to how hot you run your combustion as well for NOx, but really it's focused on the turbine stage. The other element is propulsive efficiency and how effectively we use the air to generate thrust. And you see two examples here: Rolls-Royce's UltraFan on the left, where essentially they're gearing the fan to optimize the fan speed and run the turbine at its preferred higher speed by introducing a gearbox in between. Quite a significant piece of engineering, and but some significant numbers, 20–25% have been quoted around the improvement in efficiency. And on the right there you have the CFM, which is a 50-50 venture between GE and Safran, where they're returning to the concept of the open rotor. Neither of these concepts are actually brand new. Frank Whittle sketched out a geared fan back in the 40s, and open rotors have been tested. GE did one, and also Rolls-Royce in North America. So they're, again, not necessarily new concepts, but really making that step change in technology to improve efficiency. But we're still, though, burning fossil fuel. So what's the alternative to burn? Even though we can burn it more efficiently, what could we actually do to improve the emissions and carbon footprint of aviation? So that brings us on to sustainable aviation fuel. So just to make sure that we're on the same page, what we're talking about here, I quite like these diagrams that I've taken from a study that helps sort of clarify the intent of sustainable aviation fuel. On the left, we have the traditional journey, where along the way, along each step, we're emitting CO2, and over time, those steps will be reduced. For example, if we get green shipping, etc. But you can see it's an end-to-end, and it's not a closed loop. So you're emitting carbon and creating more carbon CO2 gases, and on the right, although there is carbon released along the way, the concept is that if you can use biomass in this example, so if you use biomass, it absorbs CO2 from the air, and then as it goes through the processing, comes out the other end as a fuel, gets burnt by the aircraft, which produces CO2, and that CO2 is equivalent to the CO2 that was previously absorbed, and so the CO2 produced goes back into absorption. So this is not about not burning fuel and not producing emissions. It's about a way of balancing it. So it's a net zero solution. And some studies estimate that if done correctly, this could achieve some 80% reduction overall. So just to have a quick look at the process, and this is a highly simplified and summary of the process. So I do apologise if you were looking for something a bit deeper. But essentially, take your feedstock and you pre-treat it. Now, the feedstock can be biomass, wood pulp, waste. Some really exciting stuff being done by processing of waste and converting to fuel. The conversion process itself, and then produces SAF fuel. Then you'll notice that we're actually, the next step shown here is actually a blending with Jet A fuel, so which might seem not intuitive, but then we get what we call a drop-in fuel, and I'll come on to that in a second. So apologies about the dog in the background. So the next, the alternative approach to that is to actually generate synthetic fuel through actually generating hydrogen first. So we use green electricity, get water, electrolysis, produces hydrogen that can go into a conversion process with CO2 to produce SAF fuel. And this then again could be blended with Jet A to make sure it has the right properties, so it can be what we call a drop-in fuel. Now, by drop-in fuel, I mean that can go into an existing aircraft and an existing certified aircraft, and the fuel is certified so that it's cleared for those for existing aircraft. Ideally, we obviously want to miss out this step of using synthetic fuel, and so we actually want to just go straight to 100% synthetic fuel. And I'll just explain the slight challenge that presents us in the short term. So, so as I've said, we're showing there sort of a checklist against what the fuel properties, but there are numerous bulk and sort of more subtle properties of fuel that we need to consider to really ensure that we can actually, this is like for like equivalent to Jet A1 fuel. And it's not just about the energy content or its stability, its combustion characteristics. It's also the flash point, freeze point, density and viscosity, surface tension, lubricity, corrosivity, and all the other terms we make up in engineering. But I think just to give you a flavour of that, we could make a synthetic fuel without aromatics, and you see on the right there that the core constituents of fuel are three types of alkanes and aromatics, and those alkanes have different properties when it comes to combustion. But aromatics in particular, for example, have a tendency to produce particulates at the back end and make up smoke, and also in flight are great points of nucleation for cloud formation. So we think anyway, and so so it'd be great if we just made this, well, we're making a synthetic fuel, we might as well take those aromatics out. But if you take those aromatics out, then you're changing some of the properties of the fuel. And just give you one example, the nitrile seals used in the fuel system, if they've been exposed already to aromatics, they will have swollen, because that's the effect they have on them, and that makes a great seal. If you then start using a fuel that has no aromatics, those seals will no longer swell, and so you can't assure yourself you're going to actually have the same level of sealing. Lubricity is another factor, which is a little bit more subtle in how in the constituents that make up and give the fuel its lubricity properties. But just take, for example, the main high pressure fuel pump on an engine. There's only one of them per engine, and it operates under incredibly high pressures, huge pressure differential across it, typically over 1,000 psi pressure drop across the pumping elements, and the loads to keep the gears, because typically gear pumps and thrust face loads in particular require each company that provides them has its own unique little blend of surface treatments, but they are absolutely dependent on fuel's lubricity characteristics. So we need to retain those. So the be all or end all of SAF is that it actually could be could make a significant contribution if you can get a drop-in sustainable aviation fuel. and ideally a drop-in synthetic fuel that has all the properties of Jet A1 but doesn't involve any blending. That is really the panacea that we need to get to quickly. However, there's still a challenge in the availability of feedstock. I don't think is such a big issue in the longer term, but right now we are certainly very limited in the amount of SAF that's being produced. It's also costs more than Jet A fuel today, so we've got a challenge of ensuring airlines pick it up, take it up, and then there's incredible amount of investment to actually ramp up production and global availability. And we're going to have to, even if we want to get to 1% use of an availability of sustainable aviation fuel by 2025, we're going to have to sort of 10 times what we have today, and it's 100 times to achieve 10% by 2030. So you can see the sort of level of investments, and globally this is a sort of trillions number that we're looking at. So and just to give you a flavour for the costs of approving a new fuel, it doesn't come cheap. So each new fuel is estimated. This is estimate from the US Department of Energy, but it's over $5 million to actually clear and certify a new fuel. So covered reducing fuel burn by better use of your aircraft and how you operate it on ground and in the air, getting the efficiency up, and we've seen 2 examples where there's 2 new engines being developed around propulsive efficiency improvements, and sustainable aviation fuel, where we can make significant reduction in overall net emissions. However, if we really want to make a step change and not have any gaseous emissions, then the answer is not to burn fuel. So let's see what the options are there. So electric flight. So the ideal here would be that we use a battery to power typically a propeller. Some people prefer to try and use a high-speed fan, but whatever means you choose, great steps forward have been made. We're seeing a gradual increase year on year in battery technology, and some new battery cell compounds really being brought together to improve battery performance. However, realistically, right now, to help solve the problem, we're looking at a limited range. Now, this example here, where they've flown the 288, I think it was, miles. I don't think that'll be a certifiable distance, but it certainly shows what is possible as far as that's a good combination of I think intelligent use of battery, motor, and propellers. This one has 4 propellers, each with individual motors, and then a 5th motor propeller combination. And that looks like the first 4 are for vertical takeoff, and then the rear one is for forward motion. But how far this can really go, I think, is summarized by and ignoring all power electronics and all the other and motors. This is just comparing a very simplistic comparison between fuel and battery. Fuel specific energy is about 43 megajoules per kilogram, and batteries, you know, the automotive ones right now is probably closer to the 0.8. Some proposals are claiming 1.6 megajoules per kilogram, but you can see, though, whichever number we want to go with, we're still significantly a long way off. And the way I kind of really crudely say it is, if you had a kilogram of fuel to burn, you need 40 kilograms of battery. And of course, the advantage of fuel is once you've burnt it, it weighs nothing. The battery, a dead battery, still weighs 40 kilograms. So that's the kind of the challenge. And I think we'll see these probably actually not. I've used the units of people for 200 miles, but I think in reality we'll see these aircraft predominantly initially around ferrying cargo, but some exciting opportunities, but not really addressing the big issue. And if you remember the diagram of what, you know, the 7% versus 93% of where burnt fuel is. That's really, we're not getting into the big area of long haul and short haul aircraft. So electric flights, so you can, so the hybrid electric, I remain curious and open-minded about these combinations. There are various combinations when you talk hybrid electric. It's often involving sort of trying to compensate for the battery's limitations by either having ways of charging it during flight, or adding gas turbines and taking some of the pain from the with the batteries, and then complementing with gas turbines. So you have your generators on board to generate and fuel cells in combination. And I do bring it back to one of my earlier comments about the drive for simplicity. I do find some of these systems look rather overcomplicated and heavy. So the one that I think really, really to me is much more attractive is actually the hydrogen electric. Now it's somewhat unfair because the work I've done on hybrid electric is somewhat limited. It's more reading than actually doing. But the hydrogen electric is looking, to me, looks a more promising and simpler solution. So essentially, you have hydrogen fuel, which feeds a fuel cell, which powers electrically a motor, and then you rotate your propeller. So reasonably straightforward concept. I think the real key here is the development of the fuel cell. Clearly, you need a supply of hydrogen, but I think for you know, initially the smaller aircraft that people are looking at, you know, hydrogen supply will be a factor, but it is, and certainly in gaseous form, a solution that can be solved. And again, I think certification I've put down there, it's just because it's new, and our certification is so built around known technology rather than new technology. It just presents some little challenges that need to be addressed. But I don't see them as stoppers. I think the key thing is getting the fuel cell technology. And one of the problems with fuel cells is their efficiency. And it's essentially, if you're not familiar with fuel cells, I'm sure you are, but crudely described, they're essentially a sort of a battery that generates electricity through replenishing of fuel, the fuel being hydrogen. So, and the output being water. So the good news is the demonstrators that have taken place already look very, very exciting. But as the power levels go up, because of the inefficiencies in fuel cells today, the heat, what we do with that heat and how we manage that heat and extract that heat is actually adding significant weight, and that is really where the barrier comes down. However, players to look out for in this field are ZeroAvia, H2Fly, and Universal Hydrogen, and some really fascinating demos. And I really like their model of having kits so that they can actually go and convert. The concept is you convert your ATR-42 aircraft, which is again looking at actually a solution that you can, through a conversion process, actually use in stored fleets. And I think that's very powerful to the argument. So we tried not burning fuel, but so far I've managed to describe aircraft that can go, say, 200-ish miles with current technology, with a relatively small cargo or handful of passengers. We've described the potential of the hydrogen electric and the fuel cell, and that is, I think, is something to watch. But I think we haven't really entered the 93% area. So we haven't really got a solution for our narrow body aircraft, and we haven't got a solution for our wide body aircraft. And so the next section is really moving into hydrogen. I haven't gone into nuclear reactors and other such ideas on planes, but there is a lot of talk again about hydrogen. Hydrogen was looked at a number of times, and the Russians and the US have done flying demos for different motivation than carbon dioxide and other emissions. But anyway, in theory, it could work. And the beauty of hydrogen is, number one, it doesn't contain carbon, so you don't get any CO2. It's also, its specific energy is superb. It's superior to Jet A, 120 versus 43, so 3 times more. But the energy density, it just needs more volume, and that is a problem. And to get even to the level of and you'll see the LH2 there. So LH2 is the liquid hydrogen, and that is one of the challenges. Liquid hydrogen means that you're storing it at about 20 Kelvin, and so you'd be storing it, and then miraculously feeding it to your gas turbine. Gas turbines run on hydrogen today. They run on hydrogen gas. Gas and vapors are the things that actually burn. So that's what you want to feed into your gas turbine. So you're going to go from 20 Kelvin to 300 Kelvin plus, maybe, in a relatively short space. Emissions wise, there's no CO2, but it doesn't actually solve NOx. NOx and hot combustion is an issue. It's really linked to the temperature there. So and contrails, because you get around about 3 times more water, although you don't get the particulates, so maybe the cloud formation won't be so bad. So there we go. The challenges I've kind of described on some of the challenges in hydrogen. First and foremost, we need a hydrogen infrastructure if this is going to work. So you can't just have hydrogen globally distributed and available at airports just for aviation. The business case for that just wouldn't exist. And we're going to, although we transport liquid hydrogen today, very few people actually store it and use it in that way. So that would be a uniqueness. There's lots of unknowns about the environment as well, and it's a fascinating area for engineers. Absolutely fascinating. Lots of challenges, and so here's my rough summary. This is very much a personalised view, and it changes on a monthly basis, I think. But the key message here is I've tried to sort of, if you look at if you take the middle of this chart and look down, that's really your sort of area that's consuming most fuel today. And really what we're looking at is that a sustainable aviation fuel, we need to really drive and focus on that and look to the sort of more longer term solutions. And at the moment, there's a lot of people pushing the hydrogen concept, which is, as I say, very exciting for engineers. Okay, so net zero engineer. I think I'd just like to explain what I mean here. So net zero to me, for a net zero business, you look after you're accountable for the emissions caused by what you do in business, all the way from your upstream supply chain into your downstream supply chain. And as a result of that, there's going to be a better understanding of which materials to use from a green point of view, from a low carbon footprint, where you get those materials from, not just from a sustainability, from a sort of environmental, but also societal perspective. And material processing, it's actually quite high in aerospace, higher than the footprint of the emissions, sorry, from the processing materials in aerospace, higher than in automotive generally. And then the manufacturing methods, transportation, in-service utilization, and then ultimately the end of life and re-life. And I think this is an area of opportunity. We could actually be more aggressive, I think, in repair and recycle and reuse. And there's also other options such as rot and minimizing what turns up as refuse. So I think this is a broadening of scope for the design engineer, and something that I think will need to come into our thinking very, very quickly if it's not already there. So that was the message there, to consider the full product life cycle. So in summary, there's no single silver bullet to address this challenge. The nearer term opportunities are operational improvements and sustainable aviation fuel. Electric will work for short-range vehicles, and regional hydrogen electric looks promising. But to make a real difference to emissions from aviation as a whole, it's going to be SAF first, and then we see where we go with the hydrogen economy going forward. But I would summarise: engineers solve problems, and what a great time to be an engineer. Okay, thank you for your time. And if you have any questions, I'm happy to answer them. Okay, so got one question here. Okay, do you think the eVTOL aircraft will be a growing market, and if so, which designs will win? Well, I'm not a aerodynamicist by any stretch of the imagination, and I'm not really a marketeer. But when I was young, I used to read Look and Learn magazines, and they had articles on history and science, and they showed flying cars all the time. So I was always imagining that by now I'd have a flying car. I think Asia is very interested in intracity travel and short-haul air taxis, and they're highly motivated by that. I think it'll be more difficult in, say, this part of the world, but I do think cargo transportation between cities is something that the likes of the organisations like Amazon and such are very interested in, and I think that's probably where the greatest opportunity lies, and also difficult to reach medical supplies and emergency rescue. How big that market is, I couldn't say. The only other thing I would say is that I see some designs where there's lots of high-speed fans, running a motor at high speed where it likes to be running a fan at high speed. But I'm curious about the overall efficiency of that packaging, especially when you have lots of fans. I prefer to see fewer propellers rather than fans. So if you have a propeller is generally more efficient at these sort of speeds than a fan, and I think and you probably have to just accept that you need to run your motor faster than a propeller. So you probably need to package a really nice, handy reduction gearbox in there. But I'm not an expert in this field, so that's just a sort of amateur's assessment. Anyway, thank you very much for your time. It's been a pleasure to talk to you at the EDS Reconnect, and I hope some of you found some interest in there. Thank you.